So hi, thank you very much for letting me talk here because I'm not working on cancer but on HIV. But today I will present individual prediction using mechanistic models based on ordinary differential equation essentially. So first I will explain what is a mechanistic model in my vocabulary, and then we will see how to do inference and prediction and build confidence interval for the individual predictions. So let's first see examples, because instead of giving you the general theory, I will give an example on HIV to illustrate it. So in mechanistic model based on ordinary differential equation, you must have some compartment of cells. And for example, in the HIV context, the cells of interest are the viruses and the CD4, which are immune cells, which can be quiescent, activated, or infected. Basically, if you want to do the same in cancer, it's exactly the same. You have to define some population of cells and write a differential equation for each compartment, which will describe the dynamic of the compartment and the mechanism between each compartment. So you have to exhibit a relation between a quantity and its changing rate over time. Let's, for example, focus on the infected cells. So the infected cells in my model are created by a low mass action, depending on the number of viruses, the number of activated cells, and a biological parameter, which is the infectivity. And then those cells can die at rate μT star. So that's my system of ordinary differential equation, and that will be my mechanistic model. So at the end of the day, I have the target cell model with 4 ordinary differential equations. And if you want to do the same in cancer, you can write a model, but you must remember that mechanistic model rely on a transcription of physiopathologic knowledge of the disease. And if you don't have the real mechanism that is behind the dynamic, then it will be very difficult to fit the data and also to have good predictions. So now I want to use data and real data for real patients. So there is no reason why the parameters should be the same from one patient to another patient. That's why on each parameter we will use a statistical approach and a statistical model based on a mixed effect model to say that each individual parameter for patient I will be a sum of fixed effect, potentially depending on covariates, and random effect, which are there to model the inter-individual variability. And those random effects are really important because it's thanks to that we will be able to do prediction and individual predictions. Then we will have some observation. So for example, here we will observe not all the compartments of the mechanistic model, but only some combination of compartments. For example, in HIV, we observe in routine the viral load and the total number of CD4. Then we apply a transformation in order to ensure the normality and the homoscedasticity of the data. And then we can say that we have some observation plus an error measurement. And this error measurement will be supposed to be Gaussian. So at the end of the day, in the ordinary differential equation-based mechanistic model, we will have a lot of parameters to estimate. That's exactly what Adeline said. And we will have all the fixed effects, all the random effects, and all the measurement errors. So the estimation is possible, and I'm very glad that Adeline did a very nice description of the estimation techniques, so I can go faster on this point. So first of all, we want to do estimation, but our final aim is to do prediction. So I must insist on the fact that we must build a learning data set and exclude all the patient and at least observation that we want to predict. So it's quite intuitive, but we must do that in the estimation step. Afterwards, we can use estimation techniques, so that's not the point today, but there is some techniques which are based on non-parametric analysis, but there is no real software to do that in routine. So maybe it's better to use more traditional parametric analysis so like FOCE in air, for example, but this is a non-Bayesian technique. And in mechanistic models, the problem is that there is a high number of parameters to estimate. So sometimes you don't have enough information in your data. So you must use a prior information. And then you must switch to Bayesian techniques. So Bayesian techniques, there is a lot. There is the SIEM Bayesian implemented in monoliths, but also classical MCMC that you can do in Winbergs. And there is also a technique based on penalized likelihood and a normal approximation of the posterior that is developed here in Bordeaux. And it's based, the software is called Nimrod, so it's quite difficult to use because it's written in Fortran, but you can download it and it works well. And we've shown that in highly parameterized model, sometimes it's less long to run and give better estimates than other techniques. So you can try it. So now we are to the point. We did the estimation on a learning data set, and now we want to do individual prediction. This is possible. So let's, for example, see here the example for viral load. For a specific patient I, we have a knowledge and information that we will denote rounded f till time j. So here we have 4 observations. So what we want to do is to find the individual parameter knowing the information for the specific patient I, and then we will inject those parameters in an ODE solver in order to have the predicted trajectories. So this is possible. CAS developed on the parameter empirical bias that allow to do that. And basically, it's just to say that the individual parameter will be the sum of fixed effects that were previously estimated on the population. And then we have to update the random effects for the specific patient by taking the posterior mode of random effect, knowing the information till time j. And this is possible, and computationally, it's the same as computing the maximum of individual likelihood, taking into account only the observation of patient I till time j. So once you've done that, then you can inject it in ODE solver and have the predicted trajectory that we will call y hat. But now we want to assess if the prediction is good. So there is a lot of indicators like mean square error, indicators that can give some hint. But we can also want to draw some confidence interval because it's more graphic. So as far as confidence intervals are concerned, there is 2 kinds of uncertainty in this mechanistic model. First kind of uncertainty is estimation uncertainty, because we did a 2-step estimation, first for fixed effect and also to update the random effects. And then the second kind is uncertainty in the error measurement. So let's first begin with the first kind of uncertainty. We are working with a huge mechanistic model most of the time. This one is a little simpler maybe. And most of the time, it's not simple to have an analytic expression of the solution. And when it's nonlinear, sometimes it doesn't exist. So we must do something. So what we want to do to have a credibility interval, which is a credible interval like in Bayesian theory, is to sample the post-sum realization from the posterior distribution of the individual parameters. And this is possible by sampling for the fixed effect on the normal low. Either you can do it classically with MCMC, but it's quite long to run, or you can make a normal approximation. If you do the more normal approximation, you just sample the fixed effect from the normal low that you previously estimated in the first step, and then the random effect from their updated low, knowing the information that is available. And then you have sampled the posterior distribution, and by injecting it in a solver, you can have the posterior distribution of the predicted biomarkers for patient E, knowing the information available. And here it's in dashed line, so it's here. But this kind of confidence interval only take into account the estimation uncertainty. And we know that when we have observation, there is some observations that are maybe outside the range, maybe also because error measurement, or because of daily variation, for example, for CD4. So another kind of credible intervals that you can build is measurement error intervals. So in fact, it remains in saying that our observation follow a normal law, but we estimated in the first step the measurement error in the population for each compartment. So then we just build a classical confidence interval. And this will give the shaded zone here. So what you can notice here is that when there is few information about the patient, here we only took one observation to do the individual prediction, then these two confidence intervals are quite the same. So after all, we can also build a confidence interval where we mixed the two kinds of uncertainty, and it just remains in saying that our observation will follow a normal law, but the variability will be the same of the variability for measurement error plus the variability for estimation, and we can just take the empirical variance of the sampling of the posterior biomarkers. So at the end, it's no more that the dotted line, which is this predictability interval, which take into account uncertainty in measurement error and uncertainty in estimation, is bigger than the two other ones. But it's nice to compare all those confidence intervals in order to see if our prediction is good or not. So to finish, I just want to show you that the comparison between those intervals, and especially between the credibility interval and the error measurement interval. So on the upper graph, you can see that we used only one observation to draw the individual prediction and the confidence interval, whereas on the graph in the bottom, we used 5 observations. And we can see that first, the predictions are better when we use more information, so that's pretty fair. But we can also see that when we have a lot of information on the patient, then the credibility interval becomes narrower and is smaller around the data, whereas the error measurement is still the same because it was estimated before on all the data and all the population. So we think that when you are looking at prediction and personalized medicine, for example, it's quite nice to look at estimation credible interval, but you must not forget that the error measurement interval is really bigger. So just as a conclusion, I will say that parametric empirical bias are really useful in mechanistic models to do predictions, and predictions are also really good because when you look at prediction, you can see whether your model is mechanistic enough. Because sometimes you can have some model we will fit the data, but predictions are really bad. So if it's not, then maybe you must have some compartment to your ODE model or try to find another model. And then it allows us to account for measurement error and estimation uncertainty. And to finish, I will say that this kind of prediction is particularly interesting in personalized medicine, and thanks to that we developed some optimization treatment strategy in HIV, and it's also maybe possible to choose the best treatment for the patient. For example, if we have some data, we can forecast how the patient would react to various treatments, and then according to clinical outcomes, you can choose the best treatment for the patients. So I would like to thank my supervisor, colleagues, and all funding institutions. And if you are interested in estimating parameters in mechanistic model, just you can send me an email or look at the website. There is a software, and in personalizing medicine in HIV using this kind of prediction based on parametric empirical advice. There is 2 articles based on that. Thank you very much.